He did it. Crazy son of a bitch did it again. What am I talking about? Jürgen Schmidhuber, reinforcement learning upside down. New paper just dropped on the verge of the NeurIPS conference, being presented at a workshop here. Presenting upside down reinforcement learning. I am pumped for this one, can you tell? So, it says we transform reinforcement learning into a form of supervised learning by turning traditional RL on its head, calling this RL. LAR. What are we gonna call this? We'll just call it LAR. Upside down reinforcement learning. And so this is upside down. I mean, what is this? Never mind. Okay, let's just check out how it works. So I'm going to give a brief overview before we gonna go into this paper. All right. So let's say you have a reinforcement learning problem. Let's say an Atari game, for example. And in an Atari game, you usually have a screen, right? And let's just say you're playing this marine commander. So there's water here, right? And there might be a bunch of here's your boat, right? There's a boat, a little boat. There might be a bunch of opponents right here, fishy fish opponents, and so on. Then there are a bunch of gold coins, like here. Oh, that's a big gold coin, right? And you're kind of supposed to, I think you're supposed to like go get air. You have some air meter over here, whatever. So there's this Atari game, right? Are supposed to get the reward, which is this maybe this coin here, and stay alive as long as possible, and so on. So this is a classic reinforcement learning problem, and there are various techniques for this. We've looked at a couple of them. And what upside down reinforcement learning does is basically what you do is you want to transform this input to a new representation, which basically, well, if I can, maybe I can. Let me get this correctly. So, and then there's this over here, and then there's a little fishy here, and there's a coin right here. So what you want to do is basically turn this input on its head, like upside down, and so this way is kind of up or down, or whatever, in this new representation. And if you actually learn on this new representation, with pretty the same techniques, it works much better than the classic RL setting. And this is not only for like these Atari games, like this appears to hold throughout the RL space. So in robotics, like if you have a robot, whatever, this is a robot, it has a square head, as you can tell. It's supposed to like open a door. You've seen this DARPA challenge, this doesn't work, right? But if you just transform this and actually turn the robot upside down, the robot will be able like to open the door just fine. And even like if you have a chessboard and there's like a bunch of pieces on it, the problem in this case is you have to so you need to simulate this chessboard, and if you turn this around now, you basically all the pieces will fall off. So what you need to do is you need to have a simulator that encodes a magnetic chessboard such that the pieces don't fall off. But so it's a bit of programming effort, but if you do that, all right, I'm kidding. It is a new paradigm for RL, but it's not as good. Though someone should try the magnetic chessboard simulator. Upside down RL is a new paradigm for RL where basically the kind of notion of inputs and outputs of the RL algorithm are switched around a bit. So basic ideas here is that you have an RL algorithm that is also fed with a bunch of commands. So in classic RL, what you'll have, and let's actually go back to this Atari game here, right? In classic RL, an RL algorithm will get the Atari game the screen as an input, and is asked from this to predict a bunch of outputs. So in classic Atari, these are 8 actions. I'm going to draw 3 here, like go to the left, go to the right, or press the button for shoot. right? These are the actions you have, and the algorithm is tasked, and there are different versions of this. In policy methods, policy gradient methods, typically the algorithm is tasked with outputting a distribution over these actions. In other methods like value learning, Q-learning, the algorithm is tasked with assigning each of these actions a value. So it's in this situation, going to the left will be worth 3 in the future. This going to the right will be worth -1, and shooting will be worth 0. So you might want to go with this action here. Right. Now in upside down reinforcement learning, so we've had observation going into the model, and the model coming up with the value estimation of the different actions. Right. In upside down reinforcement learning, you'll have the observation and something else going into the model, and the model coming up with an action. Right. And this something else is the key. What you input here is your desire, your future desire, and in this paper they call it a command. So you'll have a command as an input together with the observations. You basically say, here's my state, and I would like to achieve, let's say, 5 reward in the next 2 time steps, right? Make this happen, right? This is your command going into the model, and the model will then try to find actions such that in the next 2 time steps you'll get 5 reward. You can easily see a model that learns this will actually be able to do various things, including doing the classic RL things like get as much reward as possible in a given or in the shortest amount of time, but can also do much more. And in the general sense, the difference is how this is trained now. This model, when you train it, as you can see, it's not trained with having in mind kind of only to get the maximum reward. It is trained to be much more a general kind of understanding of the world. I mean, learning what do I need to do to achieve a variety of goals. Specifically, what you want to do to train this is the following. Say you have a method of moving in the world and collecting traces, right? So you go from state 1, state 2, state 3. You go with like here, action 1, action 2. Let's draw action 3 to state 4. And in each of these you get rewards, right? Reward 1, reward 2, reward 3. Now this in classic RL, this will kind of give you one training example, right? So this is if you consider this to be an episode, this will give you one training example to run this sequence of actions. Upside down RL, you can actually consider this as many training examples, and here's what I mean. So if you, for example, start at state 1, you can say, aha, within one time step, I go to state 2, and I have achieved R1 rewards by doing action A1, right? So this now can be an input to your model. Your model could learn. If you get as an observation, you remember the previous thing, as an observation, you get S1. As a command, you get, I want to achieve in one time step R1 reward, right? And you train, this goes into the model, and the model is trained to say A1. Given if I am in S1 and I do A1, I will achieve that, right? So you train the model to give A1 as an output. And this is valid because in the past you've observed going from S1 using A1 to a state where you get this this kind of reward in this kind of time, right? But you can also, so you can do all of these single steps. They will all provide individual training examples to your model, right? But then also you can consider a two-step thing. So you can say, I'm in state S1, and I go in 2 time steps. I have achieved R1 plus R2 reward by doing actions A1, then A2, right? And A2 I'm going to do in parents here, because what you want to do is you want to always consider the action that comes right after where you are now. So again, your training sample, let me draw this up here maybe. Your training sample would be the following. I am in state S1, this would be my observation. My command would be, I would like to achieve in 2 time steps reward R1 plus R2, reward, right? This reward. This both goes into the model, right? You tell the model, please, given the state S1, achieve this reward in this time, and the model is supposed to output A1, saying, aha, in the past I was in this state, and I did achieve this goal by using that. So the model is supposed to learn to achieve different goals, right? So now you can not only train from good episodes, right? You can train from any episode. Usually in classic RL, you kind of want to focus on the good episodes because you want to maximize your reward. But here, you can tell the model, hey, if you've done something particularly stupid, let's say here in S3, you done something, the A3 was particularly stupid, gave you, so R3 here was a really bad reward, like a negative 5 billion trillion. And you can actually train the model to recognize this. Can say, hey, look, if you are in S3 and within 1 time step you want to achieve negative 5 billion trillion reward, all you have to do is action A3, right? And then the cool thing now is, if you are at evaluation time, you actually want the big reward, what you'll do is you simply plug in a different command. You simply, in 1 time step, still I'm in state S3, in 1 time step, I want to achieve actually 3 reward, not negative a lot, right? And the model will have learned that A3 will lead to a situation where you get a lot of negative reward. So the model will be like, I'm for sure not going to do A3, right? I'm going to do something else here because I have learned to map A3 to like this really low reward. So in essence, this has connections to things like hindsight experience replay and kind of universal value function, where you kind of learn to go from any state to any other state in this, but none of these have this kind of command, what the Schmidhuber calls command here, as an input to the model. And I think actually this is really positive to input this, because usually in universal value functions, what you would say is, let's consider a simple grid world, right? Whatever, your agent is here, and you need to reach a goal that's down here. But you might not be able to learn it because it's super sparse reward and so on. But what you can do is you can learn to reach this position and this position and this position from various positions, like go here, go from here to here. You can learn to go from here to here. And, in essence, you would like it eventually to generalize to all the fields. So you basically learn to go from any position to any other position with your agent. With these universal value or universal policy functions, having sub-goals. But they, during that phase where they learn to go from anything to anything, they don't necessarily include this reward thing as an input. It's more like kind of either a sub-goal or like the value function will simply approximate the reward. Whereas in this technique, we actually have a policy learning. We actually output an action value. Also, hindsight experience replay. What hindsight experience replay would do in the same situation, right? You're here. We might do videos on this in the future. You're here and you try, right? And your agent actually, it ends up here, right? Ends up right here. What you can do is you can simply say, oh, well, actually this was my goal all along, and then simply train train your model as if this thing here was your goal all along and not this thing here, and treat it as kind of a positive reward for this. At least that's how I understand it. Right. And both of these things are quite different than here, where we have this command as input, and I do like it. So I think this is very much the basic things. Here it is extrapolated to kind of noisy inputs, noisy environments, and so on. But this is the basic gist of it. So here you see what you will learn is to map all, and all is your representation of your input, so the screen, for example, or the chessboard, and I think also kind of the last action and the reward you get in this step, plus your horizon and desire, so in how much time you would like to achieve how much reward. And then you can also input some extra goals that you have. And so you can see basically any episode that you've run in the past will give you a valid training example for this. Your model will simply learn to match the previous experience with the goals that were achieved in the previous experience. So there is lots of generalizations here, like how exactly these things are represented. This time horizon can be a high-dimensional object. The desire can be, as I understand it, somewhat a high-dimensional object. The extra commands can be like conditionals on these two things. It gets very complicated, but I want to jump ahead to a different paper so this paper is basically just describing the algorithm, and then the next paper is doing experiments with this. Let's scroll past here. All right, so this paper, Training Agents Using Up-Down Reinforcement Learning, released on the same day, but different authors that have used, Schmidhuber is also here, but have used this to now implement a variant of this. And here you see again what I was trying to explain. So in traditional RL, this is especially here Q-learning, you'll have this function which gets an observation as input, and in Q-learning especially you also get the action as an input, and you're supposed to say, for the given observation, this particular action has this expected value as a return. Right? That's what I explained at the beginning. That's kind of value-based reinforcement learning. Whereas the behavior function here, which would be upside-down reinforcement learning, gets the observation and a command and will map that to an action. And here again is what we've gone over. This is a bit of a different thing. So this agent has apparently run 2 different episodes. One point it did this sequence of actions, and at the other point from the same starting state it did this sequence of action. And you can see here on the right all the training samples we can derive from this. So we can say from state S0, right, if I want to return in one time step, I have experienced this in the past, right, to return in one time step, all I have to do is take action A1. Right? But if I want one return in one time step, I have to take action A2. Right? And you teach your behavior function to learn these things, to learn to output these actions with these things here as inputs. And then what you hope, of course, is that this will generalize, that it will learn to generalize, that you can say, now give me more reward than I have ever seen before, right? And it will kind of learn which things correspond to lower reward, which things correspond to higher reward, and will be able to extrapolate which things will correspond to even higher reward. Sorry. So they have 2 algorithms, and this is kind of reminiscent of the old RL kind of world, where you do kind of one algorithm is continuously learning from the experience gathered by another algorithm. So you have one set of algorithms, and this even in modern RL, this is how it's done, right? You have two different boxes, right? Actually, you have probably one box learning the model, like this is, I'm going to represent this here, learner, right? And the learner distributes the model to many, many machines interacting with the simulators, and these machines, all they do is run episodes with the learned model, and they will send back their experience here, and then the learner can learn from it, and then at the end send it again, and so on. So all right, here we go. So in each step, what we do in order to generate a new episode, we don't always want to kind of execute one given policy. What we do is we sample from the end of the replay buffer, and the replay buffer is sorted by returns, right? So the highest return episodes are on top. So we want to sample the highest return episodes. Then we want to say maybe some of them are 10 steps long, maybe some of them are 5 steps long, and so on. So we set the horizon to be the mean of the lengths of these, right? And we set the desired return, how much return should be achieved in this time, to be the unit, to sample from the uniform distribution between m and m plus s. And m is the mean, and s is the standard deviation of the selected episodic return. So what this means is like, here's a bunch of episodes from, oh, they start at the same time. Here's a bunch of episodes that I ran, right? From here is time 0, and then time goes on, that I ran that had really high returns, right? Now I'm going to take the mean time that these episodes ran, like this. This is maybe 5 time steps. So in 5 time, I want to achieve, now how much reward? Now you look at all the rewards that were achieved. This is maybe a distribution that has some mean here, like so. And then you say, I want to achieve a reward between here and 1 standard deviation higher than here. So, right, and this would be the reward you want to achieve. So what you do is you push your learned model to just go a bit beyond what it has seen so far. You basically say, look, you can do this, but you can just do a bit more in the same amount of time. Please do this. And you hope the model has learned to kind of generalize to do this. And if so, you will execute these episodes, and then these episodes will go back to the learner, right? Will go back to the learner here, and the learner will learn from them, and hopefully then you can like generalize even more, and then you can say, I now know how to achieve this bit more reward. Now I can, if I run the episode, I will achieve even more reward. I can push the model even further, right? So at eval time, you can always ask the model to produce as much reward as possible in the given time. And of course, every episode sent back here is not only one training example, as we saw, but many, many training examples can be derived from these models, even beyond what's in this paper. All right, so I think this was a good first shot at describing this algorithm. I hope you get the gist of it. I enjoy this. A bit of a criticism for me would be it still kind of it doesn't touch the exploration dilemma. So it again deals with kind of incrementally getting better. Whereas I feel this can easily get stuck in some minimum where it's not possible to do this incremental generalization of the model where you really need a new approach. And that's why games like Montezuma's Revenge are solved using algorithms like Go Explore and not any of the classic algorithms. That being said, they have experiments where they show that especially in sparse reward environments, they do better than classic RL algorithms. So if you, for example, here take the lunar lander where A to C beats upside down RL, and I guess you didn't get matplotlib to do the upside down RL. Well, in other environments, upside down RL clearly beats the classic algorithms. And what I like here is they took a lunar lander, and which basically at every time step you get a reward in lunar lander, and they hypothesized, okay, this is really good for these classic algorithms that do reward maximization instead of kind of learning this general behavior function. And what they did is they modified the game such that all the reward is given at the end of the episode, and then you see that upside down RL will actually outperform here the classic things, where it's exactly the same game, you just get the reward at the end. So upside down RL kind of learns the structure of the world, learns that you get this reward at the end after such and such many time steps. So it will learn, please get me 0 reward in 50 time steps, like no problem, but please get me 1,000 rewards in 100 time steps, no problem, I just go to the end of the episode, right? Whereas these pure reward maximization techniques, they somehow have a harder time to do that. I like this investigation. I like the thinking outside the box, the Schmidhuberism of the paper. It's just all great. It's a great time to be alive. And check this out, and I'll see you. Bye-bye.